This is the idea behind this problem. Once more, let's do it, okay, on the slides. So this is the condition mainly of having a straight line parallel to a plane. The inner product of the normal vector of this plane and the direction ratio of this vector should be equal to 0. This is condition number 1. Condition number 2, all the points on the straight lines are not shared with the plane. To prove this, it's simply enough to get one point from the straight line, which is the formulation point, and the substitute in the equation of the plane. If it equal to 0, it means they are, it belongs to it. If not, so it will be correct that they are strictly parallel. So I will do this in 2 steps. The first step, as we saw, I will get the direction vector of the straight line and the normal vector of the plane. This is the direction ratio of the straight line, that's the normal vector of the plane. And let's check the inner product, if it's equal to 0 or not. We already checked that. They are equal to 0, so this point was checked. Okay, the inner product equal to 0. Second step, to use the point from the straight line and substitute in the equation of the plane. Unfortunately, I don't have the equation of the plane as I have 3 points. So first of all, I have to have the equation of the plane. Once more, let's get first direction ratio of the straight line. From here, I have a point which belongs to R, which is simply 2, 3, and 0. So this is the point number 1, 2, 3, and 0. And I will get a second point belongs to this straight line to avoid the fact that the vector is 0, 2, and 4, or whatever. So I can get a point belongs to it really very easy. All I have to do is to consider x equal to 2, let y equal to any value, or z equal to any value, and get y. It will make no difference. Then take x equal to 2, choose either y or z, as I told you. I will get y, I will choose y, and get the value of z corresponding to it. So this is the point, which is 2, 1, negative 4, exactly as we did. I have 2 points. The difference between them will give me the vector that I need. So now getting the difference between these 2 points, so I will have the direction vector. I will have the direction vector of this straight line. See, 2 minus 2 equal to 0, 1 minus 2 negative 2, 1 negative 4 minus 0 is going to be negative 4, exactly as we did. Perfect. Now to get the plane normal vector. How to get the plane normal vector? It's really simpler than all of this. Because in the plane, I will have 3 points. So all I have to do is to get a direction vector between A and B. I will get a direction vector between A and C. Here I get AB and BC, I believe, or AB and CA, whatever. I have them, I will make a cross multiplication. Once you do a cross multiplication, you will get the normal vector, exactly as we did, which is going to be 3, negative 2, and 1. We have it exactly the same, 3, negative 2, and 1, exactly. Now to come to the point that I will need the equation of my plane. I have a normal vector. And instead of needing 1 point, I have 3. So any one of them will be sufficient in order to get the equation of the plane. Once more, back to our problem, I will check that the direction ratio and the normal vector are their multiplication equal to 0. So here's the vector of the straight line. That's the normal vector of the plane. Their multiplication actually come to a 0, which means they are orthogonal in each other. So now I'm in between 2 cases, 2 scenarios. Either R belongs to the plane, so the normal vector is perpendicular, or R is parallel to the plane, and this is mainly the main 2 cases. In order to separate or to distinguish each one of these cases, all I have to do is to check. The point on this straight line doesn't belong to this plane. If it doesn't belong to this plane, so they will be parallel. But if they are sharing this point, it means they coincide on each other, or the straight line is contained in this plane. So now, once more, getting the equation of the plane. This is the conditions that I'm just stating it for you. I already did that several times now. So all I have to do is to use one of these points with the normal vector in order to get the equation. That's the equation of the plane. 3x minus 2y plus z and d, so it's going to come up to, this is exactly the equation of the plan, 3x minus 2y plus z negative 2 equal to 0. I will use the point which is 2, 3, and 0, and substitute in this equation. If it equal to 0, then it coincides, or this straight line is inside that plan. If not, so they are strictly parallel. So this is what we did exactly. We took this point, substituting, it's not equal to 0, so it's completely true. Also, we can check by the distance between a straight line and a plan, and that's a revision on the slide in the cases they are parallel, how to get the distance, or the case they are intersecting and also the distance would equal to 0, and these are these 3 cases once more outlined for you. I will back again to some cases between in space, so that was about the previous problem. But now if I have 2 plans, what are the cases in 3D? I will be between 2 cases actually. So if I have for P1, W1, which is the normal vector, and W2 is the normal vector or perpendicular vector on the plan B2, and the A1 belongs to B1. So I'm in between 2 scenarios actually. Either these 2 plans are strictly parallel, or they are intersecting. This is the case if they are intersecting. Or the case that P1 and B2 coincides on each other. So I'm in between the following cases. This is plan B1, that's plan B2. So either they are one plan or they are parallel to each other. In case they are parallel to each other, okay, in order to differentiate between these 2 cases, either if they are coincides on each other or parallel to each other, the normal vector of these plans will be the same. Or there is an issue with connecting them. This is the case of parallelism. Okay, if they are coincides, also it will be the same. How to differentiate between these 2 cases? Just simply get a point in this plan and see if this point belongs to that point or not. Or get a point in this plan and see the distance between this point and the other plan. If it equal to 0, it means they are coincides. If not, you will have the perpendicular distance between them. I myself would see that if I want to differentiate between these 2 cases, either they are equal or parallel, all I have to do is to get a point in this plan and to see if it satisfies the equation of the second plan. If it's satisfied, then they are coincides on each other. If not, they are parallel to each other. Okay, let's see what's in the slides. So this is the case of parallelism. This is the case if they coincides on each other. In both cases, normal vectors will be the same. So W1, W2, they have same directions. If A1 belongs to B2, which means that they are sharing points, so they have to coincide with each other. In this case, they shouldn't. For the other case, that these 2 straight lines or these 2 plans, they are intersecting. For 2 plans to be intersecting, their normal vectors, they are not going to be the same. So there is no ratio between them. So this is the case W1, W2 don't have the same direction, so they will intersect each other. Okay. And of course the distance here will equal to 0, exactly like this one. The distance also equal to 0, but here the distance is not going to be equal to 0, just to get a point in one of them and use the law of the distances between a point and the plan to find this perpendicular point. The other couple of slides are really very simple. If I want to find an angle between 2 straight lines, it's exactly like finding an angle between 2 vectors. We already taught that previously in chapter 7, how to get between 2 vectors, how to get the angle between them. All I have to do is to make the inner product between these 2 vectors divided by the magnitude of each one of them. It's similar to angle between their directions. How to get an angle between a plan and a straight line? All I have to do is to get the vector of the straight line, the normal vector of the plan, do the inner product, and then divide on the magnitudes. And it's going to be sine theta equal to the inner product of u and v divided by the magnitude of each other, and you can get the arc sine of this angle simply. Okay? It is the angle between line's direction vector and the plane normal vector. Okay, angle of two planes, it's also really very simple. Very simple. All I have to do is to get the normal vectors of these two planes, get the inner product of them divided by the magnitude of each vector. So actually, here we are using the normal vectors of these planes together. My dear students, I'm really very happy to announce that our course is now ended. This is the end of chapter 8. You have all the ideas. Please try to study well, gather all the information all together. You can't just sacrifice any of these chapters. These 8 chapters are very connected to each other. I hope you understand this lecture. I'm really very happy to see you next time, inshallah. My pleasure, and I wish you the best in all times. Thank you very much. Thank you.